Morning, everyone. Thanks for your patience. I was trying to find my couldn't find my computer charger, and I didn't want my computer to die in the middle of our lecture. Hope you all had a nice weekend, enjoyed a little bit of sunlight before it starts raining again. We are moving on to the next chapter. So hopefully you're able to get chapter or your lab 7 turned in. Last night, I had just one email, someone had an issue, but we got that figured out. So the next chapter, we're looking all at electrons. Hold on 1 second. So we don't go in order here. We kind of hop around just because of how our department feels like stuff works best together or clumps together. So we just learned about compounds, right? Naming things, writing formulas. Now we're going to sort of get into like why compounds happen the way that they happen. Like why, does aluminum always form a 3+? Why does fluorine always form a 1-? And it has a lot to do with electrons. And all bonding is going to be based off of electrons as well. Okay, so, electrons, if we refresh on, some of their properties. So they're located outside of the nucleus. They have a negative charge and they have very little mass. So adding and subtracting them isn't going to change the overall weight of the atom, but it does have a big effect with the charge. We would never change the charge of an atom by changing the number of protons. The charge is always going to be shifted because we play around with the number of electrons. So blimps, balloons, and electrons, how this all ties together. So this is a picture of the Hindenburg. The Hindenburg was a balloon that they filled with a certain amount of hydrogen gas. Why would you not want to have hydrogen gas in a blimp or a balloon or near that? Well, because hydrogen is highly flammable. What do we actually use or nowadays, right? Helium. We wouldn't fill all the balloons at a children's birthday party with hydrogen. It's an accident waiting to happen. We use instead helium. If we look at our periodic chart, hydrogen and helium, they're like really close to each other, right? They're neighbors. Hydrogen has 1 proton, helium has 2 protons. Hydrogen has no neutrons, helium on average has 2 neutrons. And then electron-wise, hydrogen has usually 1 electron and helium has 2 electrons. So it seems like it's really close together, but that small shift in the number of electrons makes it very, very reactive, or in the case of helium, unreactive. So why are certain gases inert or certain things inert like helium? And are there other things out there that are also inert like that? Yes, all the noble gases have similar properties. Why is hydrogen so reactive? And why does hydrogen exist as a diatomic element? So remember hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, those guys, iodine, those guys like to form diatomics where they pair off with themselves. So it all has to do with their electron structure, their electron configuration. So other elements that are as reactive as hydrogen, yeah, all the things in that first column have the same level of reactivity. So lithium, sodium, potassium, rubidium, cesium, those are all going to have a highly reactive property to them. The noble gases will all behave in a similar way. So when looking at the electrons, there's two different models that we're going to talk about on explaining like how electrons work. So if you've ever taken a chemistry class or done any sort of basic chemistry, you may be familiar with this thing called the Bohr model. The Bohr model is like the solar system model of the electrons. So think about, you know, the sun being in the center and the planets rotating around it. That's kind of how the Bohr model is. We've got the nucleus in the center, and then the electrons are on these tracks or rings around that. That is a very, very simplified model. We'll use it for a hot second, but then we're going to move more into the quantum mechanical model, which is more expansive. It explains everything in the Bohr model plus more, but because it explains more, it's also a little bit more complicated. So there was definitely a boom in the chemical physical expansion of science in the late 1800s and early 1900s. So Bohr, Schrödinger, and then also Einstein all worked to develop this thing called the quantum mechanical model or quantum mechanics. It's a very sort of bizarre concept. We're not going to spend a whole lot of time on it. If you want to learn more about it, take a higher level physics class. But it has this idea of what we call the wave particle duality of an electron. So an electron in some instances will behave like a wave, and in some instances it'll behave like a particle. And a lot of times when it's behaving like a wave, there's sort of an infinite possibility. When it's behaving as a particle, it's got a very specific path. And both of those things are sort of simultaneously happening. Wave when we're not observing it, particle when we as an observer are watching it. It's very strange. So this first part sort of jumps around a little bit, but electrons will, when they're moving around in the atom, they'll give off energy or radiation, usually in the form of light. So light is a type of radiation. We need to talk about the electromagnetic spectrum and radiation. So light has a very constant speed of 3.0 times 10 to the 8 meters per second. That doesn't change. Light, just like electrons, has both the properties of waves and particles. Light is a form of the electromagnetic spectrum or electromagnetic radiation. It's in a very narrow window. So when the surface of water is disturbed, waves are carried or are created that radiate out from this central thing. The waves carry a certain amount of energy, right? So light has this same sort of thing. Depending on what color the light is, it packs a different amount of energy to it. So let's say this little raindrop here is super small. The wave that it produces is also going to be small. It will carry a small amount of energy. But if this wave becomes bigger or more frequent, we're going to have a larger amount of energy packed in there. Same thing happens with light. Red light, I'll show you here, red light has a much lower energy than purple light because of its wavelength. So what is wavelength? Wavelength is the distance between crest and crest or trough and trough. So when you have that repeated pattern. So if you had like some ticker tape, every time it hits at the top or hits at the bottom, that would be considered one wavelength. It has this kind of funky little H shape or what we'd call a lambda. As this thing gets longer, we classify the wavelength as being bigger, right? If I say bigger, I mean longer. So light has a property of wavelengths. It also has a property of particles too, though, which I know sounds very confusing, and it is. So white light, which is, when we talk about white light, we're talking about light that comes from an incandescent light bulb or from the sun. It contains the full spectrum of wavelengths within it, or all the colors, right? If I take natural light or light from a light bulb and I pass it through a slit and then put it through a prism, it opens up into a rainbow. You see this happen if there's, raindrops at a certain angle, you can see a rainbow in the sky, or if there are raindrops collecting on your window or something like that, you get Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. all of these light, different colors within white light have their own wavelength. So red light has a wavelength of about 750 nanometers. So a nanometer is very tiny, 1 × 10⁻⁹ meter. Red light is the longest wavelength. Violet light has a wavelength of about 400 nanometers. So, almost half the wavelength of red light. And then all the other colors sort of stick in between there. So just a sort of interesting thing. As far as when you look at an object and you see the color, so this woman's shirt here is red, right? Why the shirt is appearing red is because the specific chemical properties of this shirt are absorbing from the sun. They're absorbing every color except for the red. So it's sort of like the shirt is every color but red. The red color is being reflected off of this shirt, and then it's being received by your eye. So you can kind of think of this shirt as absorbing all the other colors of the rainbow and spewing red back out to you. That's why when you have certain colored shirts, if you go under natural light, they may have like a specific color to them, and then you go under black light and you lose that color, or if you go into a dark room, they'll lose that color. It's because the light that's coming off of it, the color that you're used to seeing isn't in that light source, so it can't reflect off of the shirt. So along with wavelength, we have this thing called frequency, and frequency and wavelength are inversely proportional, which means as your wavelength gets longer, your frequency gets shorter. Frequency, which is sometimes represented by a V, the sort of V shape, or a cursive V, which we call a nu, is defined as the number of cycles or the number of crests that pass through a stationary point in 1 second. So if you have a really, really long wavelength, you're not going to get a lot of cycles passing through, right? If you have a very short wavelength, you can pack more cycles through in that given amount of time per second. Again, the shorter the wavelength, the higher the frequency. Now, along with frequency, we can directly talk about energy. So each like light particle, we can call it like a stream of particles. Each particle we're going to call a photon, or like a packet of light. So these light particles, again, are behaving like particles, but also behaving like waves. The wave part of this photon comes that each photon carries a specific amount of energy. How much energy does that photon have? It's dependent on the wavelength of that given photon. So if that photon has a shorter wavelength, it is going to have a greater energy. If it has a longer wavelength, it's going to have a lower energy. Energy and frequency are directly related. Energy and wavelength are, again, inversely related to each other. So think about if you're in like a wave pool and you have a really, like they've got it set at a really long wavelength, and you're sitting there with a, I don't know, a martini or something, or a margarita, and the wavelength is coming by and it's really long. The effect on your body isn't going to be very dramatic, right? You're going to go up and then you're going to come back down. If the person decides to increase the frequency by shortening the wavelength, the amount of energy or jostling you're going to experience is going to increase dramatically, right? So instead of having these really long, dramatic wavelengths, you're going to have these short wavelengths. You're going to go up, down, up, down, up, down, up, down, up, down. And you're going to have a little bit more of this jostling. Your margarita is going to probably fly out. So violet light, which has the shortest wavelength, carries the most amount of energy in a given photon. Red light has the lowest amount of energy. If you are familiar with like any sort of Eastern Buddhist chakra stuff like that, they also have this sort of understanding that the light system, along with the chakras, red being at the base of the spine, that has the lowest energy, violet being like above the crown of the head, which has a higher energy. So let's look at the full electromagnetic spectrum. Light makes up a very narrow window right here. Okay, so if this is the entire electromagnetic spectrum, light sits, natural light sits right here, visible light sits here. On the lower energy side is the red, on the higher energy side is the purple. If we were to expand this out, you can then see all the colors. So you do need to have these, you do need to know them and the ordering of them. I don't want to say memorize because you can kind of reference it, but you want to be able to read this. So on here where it says low energy, you also want to put large wavelength or long wavelength or big wavelength and low frequency. Over here at the high energy side, you want to put short wavelength, and you also want to put high frequency. And I know this is like, what does this have to do with electrons? It will come back around to electrons, I promise. Specifically this visible light section here. But so let's go outside of the visible light spectrum. What happens if we are just slightly longer than 750 nanometers? We move into this thing called infrared radiation. And you don't have to have the specific numbers memorized for the wavelengths, but you do want to know the ordering. So infrared radiation, not something that we can see with the naked eye, right? Our eyes fall within this range of what we can see. Infrared, though there are some animals that can pick that up. Everything as you move in this direction is biologically harmless. So infrared radiation, our bodies give off that sort of heat and we can pick it up with certain goggles. This isn't going to have any sort of effect on our skin or DNA or anything like that. Much larger than infrared or longer wavelengths are microwaves. Microwaves are what are used for cell phones, some TV, and then also what's in microwave. What's interesting about a microwave is just the right length to penetrate something and spin water molecules. So it's just long enough that it can move through and then just like kind of bang on all the water molecules in a material. And when it bangs on these water molecules or causes the water molecules to spin, it creates kinetic energy, which heats things up. So that's why your microwave works. It's because the microwaves in your little microwave are hitting the water molecules and causing the food to heat up. That's why if you put something in the microwave that doesn't have water in it, it's not going to have the same effect. It won't heat up. The longest wavelength we have are radio waves. Those stretch out really, really far, 10 to the 5th, right? So 10 with 5 zeros here. And those are what you think of them as being radio waves. Let's move in the other direction. So let's say we've got radio, microwave, infrared. We go through the visible light spectrum all the way over to violet. Well, what if I shorten up my wavelength just a little bit more? We move into this place called ultraviolet radiation. And ultraviolet radiation is what is produced, or one of the rays that are produced from the sun. It's what gives you a suntan. As you move in this direction, these photons are gaining energy, all right? So these become a little bit more detrimental to biological cells as you move in this direction. So, you know, if you're sitting under violet light, it's not going to do anything to you. But if you sit under ultraviolet radiation, it'll give you a tan and then it'll start to turn into a sunburn, right? And if you spend too much time, it can actually give you cancer, skin cancer. So these higher energy wavelengths can start to break down biological cells. If we move even farther over, we move into X-rays, and those are what they use in a doctor's office to take an X-ray. X-rays, higher energy than ultraviolet. You don't want to get an X-ray every day of your life, right? Even when you do get an X-ray, what do the people who are giving you the X-rays do? They go stand behind a lead wall or a concrete wall, And usually they give you a piece of lead to cover your special areas because this specific wavelength is very good at getting into like gestational cells or eggs and sperm. So you want to keep the X-rays away from the important stuff. If you were to receive X-rays on a regular basis, it would again cause some issues with your cells. If we move even higher energy, even smaller wavelength, these guys over here pack a lot of bang for their buck. These are known as gamma rays. And you may have heard the word gamma or gamma ray in association with stars, and that's exactly what we're going to see our biggest source of that coming from. You can also get gamma rays from like nuclear decay, so radioactive power plants or nuclear bombs and things like that, but stars tend to be the biggest source of gamma radiation. This stuff you do not want to be exposed to. This will take you out pretty fast. And then we don't have anything that we know of outside of that spectrum. So these slides sort of go through what we talked about. We can move through all that. All right. So I want you to arrange these three types of electromagnetic radiation in increasing order. So we've got visible light, X-rays, and microwaves. I want you to put them in increasing order. That means start with the smallest and go to the biggest of wavelength, frequency, and then energy per photon. So if I were to have a photon of visible light, X-ray, and microwave, which would be the lowest, and then increase from there. I'll give you all just a minute for that. Okay, so when looking at these, first thing is wavelength. So we're going to go from shortest wavelength. So shortest wavelength would be X-ray, then visible light, then microwave. Now, if you can do the wavelength, frequency and energy are just going to be the reverse of that, right? Frequency, how often are you going to see them? Well, the shorter the wavelength, the more prominent the frequency. So our shortest frequency or the lowest frequency should be, oops, now I've confused myself. So wavelength we said was, shortest was X-ray, visible light, and microwave. So frequency is going to be microwave, then visible light, then X-ray. And same thing with energy. Microwave will be the lowest energy, visible light will have more energy, and then X-ray will have the highest energy. So you want to be able to put those in order, and then also know like colors. So green has higher energy than yellow, things like that. Okay, so as far as how this whole thing with like electromagnetic radiation and the visible light spectrum and how that applies to atoms. Well, if we look at, this is a light with a tube of neon, and then in the center, that's not neon, that's probably, it's blue, mercury is blue. So when you excite the neon that's in this tube, and how are we exciting it? You have to plug it in, right? This doesn't glow on its own. You have to give it some sort of energy source. So when I plug this in or I excite it, the electrons in each of the neon atoms are going to sort of expand to a higher energy shell, or they get excited and they like move away from the nucleus. When they relax back down, they produce light, and specifically they produce this sort of reddish color. So each atom will produce its own sort of color and or light spectrum. So mercury forms a bluish color, hydrogen will form a pinkish color. If we were in a lab setting, we have a couple of these vacuum tubes with different gases in there that we plug in, and they produce a bunch of different colors. If I was to take those colors, so like let's say we took the neon and we took the hydrogen, and we aren't going to do mercury, but helium, we've got hydrogen, helium, and neon, and we were to put it through a prism, this is what the spectrum would look like. Okay, so natural light or white light, remember we get the full rainbow. So we get every single color because white light has all energies, energy photons within it. When we're looking at a specific element, we're only going to see these discrete lines at specific colors. And this is sort of like a fingerprint, because any hydrogen, wherever you find it in the universe, if I was to excite it and then pass that light through a prism, it is going to have these specific lines. Helium, we can see it has a few more lines. Neon has quite a few more lines, right? But it still doesn't have the full spectrum. Why are we getting these very unique or specific lines? Like, why does hydrogen have one at this sort of reddish orangish, at a blue, at a purple, and then at like a deep purple? Well, let's talk about what's going on there. So we've got our light source, we run it through a prism, and we've got these very specific lines. All right, so how this plays into the Bohr model. Well, Bohr saw this and decided, okay, what's happening is there's electrons and they're getting excited. They're moving to a higher, what we call orbit. And then when they relax, they're releasing energy. So this is the simplified Bohr model that I call the solar system model sometimes. So we've got our nucleus in the center, and then there's these sort of onion layers. And the closer you are to the nucleus, the lower energy you are. So the first onion layer is n equals 1. The next onion layer is n equals 2. Then we've got n equals 3, so on all the way to n equals 7. We call these things orbits. And the electron will circle around this track. In the Bohr model, you'll always fill lower energy before you fill higher energy. Why is it lower energy closer to the nucleus? Well, remember, what is an electron's charge? It's a negative, so it's going to want to sit close to the positive nucleus. So an electron isn't going to just casually sit in the 4 if the 3, the 2, and the 1 are open. It's going to want to sit in the 1, right? We'll fill this shell first, or this orbit first, and then we'll fill the outer shells. So what happens to create this sort of spectrum here is if we have an electron sitting, let's say right here, and I plug this thing in, that electron is going to get excited. Oh, it's got all this energy. And what's going to happen is it's going to shoot up to, let's say, the 4th orbit. At some point, that excitement will relax back down. So let's say that the current of electricity that's running through here is now no longer affecting this atom. It's affecting the atom next to it. This electron is going to relax back down to its original place. It's not going to stay in that excited state forever. When it relaxes back down, it produces light. And the light that it produces is based off of how much energy it has. So if it's going to produce a lot of energy, it'll produce a purple light. If it's just a little energy, it'll be a red light. Each of these rungs or shells, we say are quantized. And quantized is just a fancy word for saying that you can't sit between it. Okay, you're either on the first ladder rung or you're on the second ladder rung. You're fixed in one of those places. There's no like half shells. So it's impossible to exist between any of these orbits or shells or layers in the Bohr model. So here's sort of a better picture, but like if we have the hydrogen atom, hydrogen is made up of one proton and then one electron. If that electron, like let's say we plug this thing in, if this electron gets excited, we move it up here to the second orbit. At some point, it's going to need to relax back down and it'll produce energy. Again, the energy that comes out of it is light or light emission. Now, depending on how that one electron gets excited, right? If it's excited to the first, from the first to the second, it may be when it relaxes down, it'll be red. If it excites all the way out to one of these outer shells, that's a lot of energy to get out there. To drop it back down, it's going to produce a higher energy light. So looking at this, we've got, when the electron drops down just one orbit, it produces a red light. When the electron drops down 2 orbits, it produces that bluish green. When it drops down 3, it produces that violet. So we're getting these discrete lines. And remember, we can't exist in between. So the electron is never going to go from like this place down. We're never going to go between shells down. So that's why we're not going to see anything in this section here. Right? We can only go from this rung to this rung. That color is produced. This rung to this rung will always produce that color. So we get this very specific emission spectrum, which is great, right? It's like, oh, now we can sort of explain the emission spectrum, the emission lines, and how it relates to electrons. So great success with the Bohr model at predicting the lines of the hydrogen spectrum. But it failed to predict the electron spectrum or the emission spectrum for any other element after hydrogen. So that simplified Bohr model where we've got, the solar system tracks running around is not sophisticated enough to explain the other emission spectrum. Now, that doesn't mean that it isn't still a useful model. They still use that to teach like chemistry in high school and things like that, where you have, your first shell holds 2 electrons and your second shell holds 8 electrons. But we're going to move more into the quantum mechanical model. So because it can't predict anything past hydrogen, we want to use something more complicated. So the quantum mechanical model, instead of just having numbers, right, with the Bohr model, you just had the first shell was n equals 1. The second shell was n equals 2. The third shell was n equals 3. As you go up, your energy gets bigger. Simple, right? Each shell is this sort of circle shape. It's a track, and they just get bigger and higher energy. That is not the case for the quantum mechanical model. In the quantum mechanical model, we have these things called orbitals. Sounds very close to orbits, right? But instead of an orbit, we now have an orbital. So add an ALS to the end of it. Orbitals are different than orbits in that instead of giving you a specific track that the electron follows, like a train going on a track, we now have a statistical cloud of probability on where the electron is, which is a very fancy way of saying that instead of having a track where you know exactly where you're going, you now just have an area where you can kind of guesstimate that the electron's living in there. It's likely to be found there. Is the electron always found in these clouds or these orbitals? No. 95% of the time it is. Sometimes it's not. It lies outside of that. quantum mechanics, if you're like thinking this sounds so weird, it revolutionized physics. It does not make sense to us on a macroscopic scale. It feels very strange that you sort of have a general idea where something is. But we find that electrons do not behave like particles flying through space. So we don't, like a baseball, when you throw it on a macroscopic scale or a human scale, if I throw that baseball, you know where to move your glove to catch it. That isn't what's happening on the subatomic particle scale. Electrons don't follow these specific exact paths. You actually can't know the path and the velocity at the same time of an electron. So we sort of, again, when we're looking at these subatomic particles, we're guesstimating. Like this would be the Bohr model. This baseball player throws it and the ball's coming. It's not like at the last second, the ball's just going to whoop, end up over here, right? There's a trajectory that it follows. That's the Bohr model. In the quantum mechanical world, though, the electron behaves more like a probability cloud. So this catcher, he's like got a 40% chance that the ball's going to end up where he thinks it's going to end up. Then it could, be a little bit crazy. Maybe this guy throws some curveballs, but there is a chance that that electron could end up on the other side of the park or the other side of the universe. It's a strange concept. So don't get too caught up in the idea of like, what's going on with these electrons? They're sort of in and out of existence and things like that. We're going to just talk about the shape of these clouds. Let's just assume the electrons are in these given clouds or these given locations or these orbitals. So with an orbital, we have two things instead of one thing that we have to describe it. We have a number, which is called the quantum number. Sometimes they call it N. And then we also have the quantum shell, which is a letter that pretty much describes the shape. Okay, so before we just assumed every shape was a track circle, right? And you were on the Bohr model, you were either in N1 or N2 or N3, and we didn't have to explain the shape. Now we have to add a letter that gives us like a three-dimensional shape to each of these. The lowest energy orbital that exists is the 1s orbital. Okay, so if we think about this as like onion layers, we would put electrons in this orbital first, this 1s orbital. The 1 lets me know that it's the lowest energy. The s lets me know the shape, and specifically s is shape for sphere. So ground states versus excited states. Every element has one ground state. Ground state means I haven't excited it. The electrons are in their lowest, most packed, closest to the nucleus configuration. So the ground state, lowest energy state. But every atom has multiple excited states. So if I excite like a hydrogen atom just a little bit, that electron may move from the 1s to the 2s. But if I excite it a lot, it may move from the 1s to like the 5s. So there are multiple excited states for every atom, but there's only one ground state. So this is kind of similar to the Bohr model in that as you increase the number, you increase the energy. Okay, so n equals 1 is the lowest energy, n equals 2 goes, we increase from there. So we'd fill our lower energy shells or orbitals before we filled our higher ones. I would always fill the 1s before I would fill the 2s. I'd fill the 2s before the 3s. As far as the subshell or the letter, the possible letters are S, P, D, and F. S can hold a maximum of 2 electrons. Okay, so we will never put 3 electrons in here. We'll never put 8 electrons in S. It will only ever hold 2. P can hold a total of 6 electrons. D, as in dog, D can hold 10 electrons. And then F can hold 14 electrons. Okay, those are the maximum loads of electrons in each of those given areas. As far as how their shapes look, S has a spherical shape. So it looks something sort of like this. We've got in the center will be our nucleus. And if this is for hydrogen, again, 1 proton, so 1 electron, there will be an electron somewhere in here. 98% that it's somewhere in here. It could be farther out, but usually it'll be in the sphere shape. This is 3-dimensional. That's why there's an X, Y, and Z. And it's sort of existing just somewhere around here. Sometimes you'll see these written as dot densities. So the more dots, the more probability that it exists in that space. So we would expect that electron to sort of be closer to the nucleus, less probability as we move farther away. If we look at helium, helium has 2 protons, so it should have 2 electrons. So its configuration would look something like this, right? There would be 2 electrons filled into this shell. What if we looked at lithium? Lithium, on our periodic chart, it has 3 protons, so it should have 3 electrons. Well, remember, S can only hold 2 electrons, so I would then need to move into a bigger sphere. This would be the 1s. This thing would be the 2s, and that electron would be sitting around it. So the bigger the number, the bigger the shape is getting, and they sit kind of like Russian dolls. So the 1s is the smallest little Russian doll, the 2s is a bigger one, the 3s bigger, and they fit around each other. As far as the possible numbers for subshells and how they relate to, or the possible shells and then subshells. So n equals 1, the lowest energy, 1, it only has 1 type of subshell. So you can only have a 1s. P will never exist in energy 1. P starts at the 2. Okay, so n equals 2 has 2 types of subshells. It has the S and the P. N equals 3 has 3 types of subshells. It has the S, it has the P, and it also has the D. N equals 4 has 4 subshells. It has an S, a P, a D, and an F. And I will show you how to kind of read these off the periodic chart a little bit later, so hopefully it'll make more sense. But you're never going to have like a 1P shell. The P always starts at 2. The D always starts at 3. The F always starts at 4. So this was sort of what I was talking about, but the difference between the 1s orbital and the 2s orbital, they're both S's, right? They both have that S, so they're both spheres. This is a lower energy though. This one is a higher energy. So if you look at the shape, this is a smaller sphere. This sphere is larger. This sphere encapsulates this sphere. So I would actually have the 1s sphere sitting inside of here. If we had, let's say we had 3 electrons, like for lithium, we would put 2 in this sphere first, and then we'd put the 3rd on the outer sphere. If we added the 3s sphere, where would that be? That would encompass this. We have some other shapes, and they start to get really strange. The p orbital, specifically the 2p orbital, because remember, p doesn't exist in the 1 energy. P starts to exist in the 2nd energy shell. Or you can think about it like floors in a building. In this building that we're working with is really narrow at the bottom, and it gets wider as you move up. So the first floor, the lowest floor, floor 1 or energy 1, only has S classrooms, S-shaped classrooms. As we move to the 2nd floor, we can have S-shaped classrooms, but we can also have P-shaped classrooms. Okay. As we move to the 3rd floor, we can have S-shape, we can have P-shape, and we can have D-shape. What do the P-shaped classrooms look like? They look like dumbbells, specifically dumbbells in 3 directions, X, Y, and Z. This can hold a total, again, of 6 electrons. So it would be 1 electron here, 1 electron here, you know, 1 here, and then 1 here and 1 here, for a total of 6 electrons. Why does it make these funky shapes? Well, because electrons all have a negative charge. So they want to get as far away from each other as possible. So this is the structure that is most efficient at creating the most amount of space between the electrons. Do the shapes get weirder? Oh my gosh, they definitely get weirder. Let's look at the d orbitals. So the d orbitals looks like a bunch of balloon animals, right? Again, these are pockets where the electrons tend to be. We've got these sort of 4-leaf clovers, and then we've got this like donut with a dumbbell. You don't need to have these shapes memorized. You do need to know the P and the D, and the P and the S. So no S is a sphere and no P is 3 dumbbells. D, you just need to know that there are 10 electrons. I don't even think they give a picture of the F orbitals because they're even crazier looking than this. But again, it's just the most efficient way for these electrons to stack around each other, around the nucleus. So we no longer have these nice, neat tracks that we rotate around. We've got these clouds where we hang out. So from orbits to orbitals, the quantum mechanical model, although it's kind of like, it feels funky and crazy, it explains the light spectrum of all the other atoms. So that faulty quality about the Bohr model is now we're able to explain it with the quantum mechanical model. So we like to use this, this structure. Let's talk about electron configurations and how they relate to this 1s, 2s, 3s. So an electron configuration tells you or shows you where the electrons are sitting in the different orbitals. So how are the electrons occupied in the orbitals? Now remember, you always want to fill the lowest energy first, and then you fill the higher energies. So we know that the lowest energy orbital is the 1s. It's a sphere shape, and it has an energy of 1. First floor, first energy with a sphere shape. Hydrogen has how many electrons? It has 1 electron. So we put a 1 in the upper right-hand corner. We designate the orbital that we're talking about, and then we put a 1 in the upper right-hand corner to specify that there's just 1 electron in it. What if instead, let's see, we were to do helium? Okay, helium has 2 electrons. We always fill this orbital first. So it's going to be 1s. And instead of having a 1 in the upper right-hand corner, we're going to put 2. So all of your superscripts, because these are going to get chained together, should total the number of electrons that you have, and also should total the number of protons as long as you're not an ion. Another way to represent this is to draw an orbital diagram, which looks like this. So you draw you write the orbital you're looking at. So for hydrogen, we only have an electron in the 1s. You draw a box, and then you put an arrow in it. The arrow represents, or it's kind of a half arrow, represents a single electron. So this is saying, hey, hydrogen has 1 electron in the 1s orbital. Now, there's this rule called Pauli's exclusion rule or Pauli's exclusion principle that says you can't have more than 2 electrons with opposing spins sitting in each of these orbitals or each of these classrooms. So if I was to do helium, helium has 2 electrons. I fill the 1s. I'm going to put 1 electron pointing up and 1 electron pointing down or spinning down. This opposite spin is important because it balances out the electrons within the atom. So you will want to be putting opposite spins. And when you're plugging these things into mastering chemistry, make sure you have opposite spins. You don't want to do a box where you do arrow up and arrow up. Something like this. This does not work. Okay. So each orbital holds only 2 electrons with opposing spins. And if you're thinking, well, what about the p? Doesn't the p hold 6? Well, there's a p in each direction, x, y, and z. This holds 2, this holds 2, and this holds 2. So there's 3 p orbitals within the this 2p. I feel like this gets complicated and then it gets really simple once we look at the periodic chart. So let's just go ahead and do that. So how do we fill these orbitals? So this is the lowest energy is the 1s. Then we fill the 2s. Then we fill the 2p. Then we fill the 3s, then the 3p, then the 4s. Then we fill the 3d. Then we go to the 5s, the 4p, then the 4d. And you may be thinking, these aren't in order. How do we order them? Here is, where are you? It's somewhere. Oh yeah, here is the full ordering of the orbital fill. So we always fill the 1s first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, then the 5s, so on and so on. They'll draw it like this. I hate this diagram. This does not work for me. If it works for you, go for it. Where they put the 1s, 2s, 3s, 4s, and then the p's, and then the d's, and then they go like this. And that's how they come up with it. I don't like to do that. I like to look at the periodic chart. So that's what I'm going to teach you guys. So looking at our periodic chart here, I want you to break it up into what we call blocks. So the 2 columns on the left here are known as the S block. S block. Now, how many electrons fit into an S? 2, right? And how many columns are there? 2. Over here, and helium, if you guys can, when we're doing electron configurations, just put helium over here. Helium we're going to sort of include in this area here. The 6 columns to the right are known as the P block. How many electrons does P hold? 6. How many columns are here? 6. This center part where we have the transition metals, this is called the D block. D holds 10 electrons. How many rows? 10 rows. Down here where the lanthanides are, this is known as the F block. How many electrons does F hold? 14. How many columns are there? 14. The numbers on the sides here refer to the energy level that you're at. Next to D, or somewhere around here, I want you to put N minus 1, okay? Because the D energy is always 1 minus whatever row you're in. The S and the P correspond to this number. So if I'm filling hydrogen here, I'm going to fill the 1, and then I hit the S block, right? So I fill the 1s. Helium is also in row 1, and it's, we said to put helium sort of over here. Helium. Helium is also in the 1s block. So we're going to read this like a book. You start at the top, you read across, and then you come to the next row. And you sort of piggyback off of the electron configuration that comes before it. So helium, what's the difference between helium and hydrogen? Is it has 1 more electron than helium, right? What's the difference between chlorine and sulfur? Chlorine has 1 more electron than sulfur. Sulfur has 1 more electron than phosphorus, right? So you piggyback off the thing before. So when we're trying to write an electron configuration for something, we read it like this. We go, first we fill the 1, and what block do we hit? The S. So we fill the 1s first. Let's go to the next column, or the next row rather. What do we fill after the 1s? We are in the 2, and what block are we in? The S. So we fill the 2s. What comes after that? We'll keep going over, Now we've hit the 2p, okay? Once we've filled the 2p, where do we go? We go to the 3s. After the 3s, what is the next onion layer that we can fill? The 3p. What happens after that? We go 4s. Then we bump into the D. Remember, for D, it's n minus 1. So we fill 4s, then we fill 3d. Then we go back to 4p. Now, that's a way to read the electron configuration without having to have it memorized. Now, if I'm filling, let's say I'm trying to write the electron configuration for nitrogen, I don't need to worry about any of the Ds, right? None of this stuff is applicable. We don't care about that. We're just trying to fill to this place. So I would fill 1s, then I would fill the 2s, then I would fill the 2p, but how many are in there? 1, 2, and 3. So this electron configuration is 1s2, 2s2, 2p3. Let's look at some of the basic ones. I wanted to go over that first, and we'll go back here. Okay, so looking at helium, helium is got 2 electrons, so we put 2 electrons in the 1s orbital. Its orbital diagram would look like this: the 1s orbital, a box, and we have one going up and one going down. The electron configuration for lithium. Now look at lithium on the periodic chart. It is 1 past helium. So it's going to just piggyback off of what helium's configuration is, plus 1 electron, right? So we fill the 1s2, that was helium's, and then we have to add 1 more electron, 2s, and we have 1 in there. Looks like this. So here's what helium's configuration is, and then we add an electron. If we go to carbon, carbon has 6 electrons. What is its electron configuration? So put your finger on carbon on the periodic chart. You have to always start at hydrogen, fill those until you bump into carbon. So first we fill hydrogen, which is the 1s, then we fill helium, which is the 1s, and we make it 2. Then we move to what? Lithium, beryllium, that's the 2s, and we completely fill it. And then we bump into the 2p, and how many electrons do we put into the 2p? Well, we fill boron and we fill carbon, boron and carbon, and then we're done. Do you see how here, for the 2p, we've made for our orbital diagram 3 boxes. This is the X, the Y, and the Z. So each of these boxes can hold a total of 2 electrons for a total of 6 electrons for the full P. You always want to follow Hund's rule, which says you fill them in singularly, and then you go ahead and double up. So for this orbital diagram, we hit up, down, then we hit up, up, and we would fill up here if we were to move to nitrogen, and then we would start to double them up if we needed to. So let's look at some other configurations. So going past carbon, if we go to nitrogen, right, nitrogen is 1s2, 2s2, 2p3. Up, down, that's for this first thing. Up, down, that's for this second thing. And then up, 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 that's for the 3 in this P. We always fill them singularly first, and then we double up. If I was doing a d orbital, I would have 5 boxes, which with each box holding 2. So let's try an electron configuration that is a little bit larger than some of these. We'll do it together. So I'm going to do chlorine. So find chlorine on your periodic chart. It's number 17, so it should have 17 electrons. Now, when I want to fill chlorine, I have to start at the beginning of the page or the beginning of the book where hydrogen is. I have to fill in the hydrogen, the helium, the lithium, the beryllium, the boron, all those first, all the way up to chlorine. So I'm kind of reading the book until I hit chlorine. Pull this up here, go to our periodic chart where we had it. We want to get to this thing over here. So in order to get to this, I'm going to fill first this, then I'm going to fill this onion layer, then this one, and then that. So filling those in that order, well, what's the first block we hit? The first row is 1, right? And the first block we hit is S. Do I fill that completely? Yes, right? I fill hydrogen and helium. You fill it completely until you hit the atom you want to get to. All right. After we fill the 1s completely, what comes next? Well, there's the second row, so it's a 2. And I hit the S block first, right? Lithium, beryllium. So it's an S, and I fill that completely. What comes after beryllium? I bump into the P block, specifically the 2P. Do I fill that completely? Yeah, I'm going to fill that completely all the way over to neon because I haven't gotten to chlorine yet. All right, what comes after neon? We were at the end of the row, so we have to go to the next row. The next row is 3, and we've hit an S again, right? So sodium and magnesium are in the S. We fill that completely. What happens after the 3s rather? We get the 3p. How many electrons get filled there? Well, we have to fill aluminum, silicon, phosphorus, sulfur, and chlorine, or a total of 5. Are you all seeing how we have to piggyback off the things before it? The electron configurations are going to become sort of repetitive after a while, right? Instead of chlorine, what if we did argon? Argon is right next to chlorine. Its configuration is going to be very, very similar. 1s2, 2s2, 2p6, 3s2. The only difference is instead of 3p5, it's going to be 3p6. Right? It has 6 electrons in that p shell. I'm going to do something that has a D. So strontium. Strontium's number 38. So find that on your periodic chart. We look here. Strontium lives right after rubidium. So here's our strontium. So you need to fill in the first onion layer before you can fill in the second, the third, the fourth, the fifth, right? So how you remember what onion layer to fill when, we'll look at the row you're in and look at the block you've hit. So first we're gonna fill the 1s, then we're gonna fill the 2s, then the 2p, then the 3s, then the 3p, then the 4s. But then what happens after the 4s? What happens after calcium? We've hit the D. D is always 1 less than its surrounding neighbors. So we start at 3D as opposed to, let me make that a lowercase actually. We start at 3D as opposed to 4D. Okay, 4D is down here. This would be 3D. Then we jump back to the 4P, then we come to the 5S. So filling this ordering, it's going to look like this. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, that's gotten us to argon. Let's go to the next row where potassium is. That's the 4s2, right? We fill that completely. Once we get to after calcium, we get to the transition metals. It's 3D. The D is 1 less than its surrounding buddies. That's just the way it is. Those are core electrons. Do I fill that completely, that section completely? Yes, I haven't gotten to where I need to get, so I'm going to put 10 in there. What happens once we get to zinc? We jump back to the 4 and we're in the P block. So gallium starts at the 4P. Do we fill that completely? Yes. 4P6. And then we're at 5. S, and 2. So I just have it memorized looking at the periodic chart. If you don't, you will want to get the ordering filled. So you're not filling like 3 S's before you're filling 2 P's and things like that. I want you to do the electron configuration for barium. You can do the electron configuration for barium. You probably can do them for any of the other ones that come before it. I'm not going to test you on electron configurations with lanthanides or with Fs for this class. So go ahead and give that a try. Okay, so I'm gonna try and do this one on the other page here, because then I can show you. So we're gonna do for barium. So barium's right here. So it's kind of like going through a board game. You've got to start at the beginning to get to that end point. So for barium, it starts like all the other ones start. We start in the 1 and we hit the S block. So first we fill the 1s. Do we fill it completely? Yeah, because we haven't gotten to barium yet. So 1s2. Then I go to the next row. I fill the 2s and I have to fill it completely. Then I move to the 2p and I have to fill every one of those electrons in. So 2p6. Then I move to the 3s and I fill that completely. Then I move over here to the 3p and I fill that completely. And you just fill them all completely until you get to what you need. Now we're at the 4s. It gets a little trickier here. So we fill the 4s completely, and then we move to the D. All right, the D is always n-1. So we start at 3D, not at 4D. So 3D, do I fill it completely? Yes, I'm going to fill it all the way to 3D10. Then we jump back to the 4P6. So the 4 or the S and the P will have the same numbers. The D will be 1 less. It's kind of like it's nestled in there. After we've filled the 4P, we've reached the row 5, so 5S, and we fill that completely. Then we've bumped into the D again. Remember, the D is 1 less, so 4D. Where'd you go? 4D10. Then we go to the 5P and we fill that in. Almost there. Now we're at 6. We hit the D block, S, and we fill it completely. And that is the electron configuration. Any other configuration is just this, but shorter, right? Unless we do some of these larger ones with the lanthanides. But again, I'm not going to have you do the lanthanides. So really, if you can get to the electron configuration of barium, you should be good. It's total pain to write these out, isn't it? So is there a way to abbreviate them? There is. We can abbreviate these configurations by using the noble gas that comes before it. So if we look at barium here, what is the noble gas that comes before it? xenon. So I can actually abbreviate it by saying, okay, the barium's electron configuration is going to be xenon, Xe, and you put it in brackets, plus whatever's left over, right? I've got to, it doesn't have the exact configuration of xenon. I've got to like add the additional stuff. So 6s2. So what you do is you take this whole chunk, and because that's always consistently the configuration for xenon, we just abbreviate it. You only use the noble gas that comes before it. All right, so if I was to do, let's say I was to do bromine. If I was to do the abbreviated version for it, I'm not going to use helium, I'm not going to use neon, and I can't use krypton because that's in front of it. I need to use argon. So bromine's configuration, Br, if we abbreviate it, is going to be argon plus everything else, right? That gets me to bromine. So then I've got the 4s2. I've got the 3d10, and then I've got the 4p5. If we go back to the slides here, they give another example. Sodium, right? Its electron configuration would be 1s2, 2s2, 2p6, 3s1, which is just like a lot. You could abbreviate it by using the noble gas that comes before sodium, which is neon, and then just add whatever little electron giblets are still left around. Okay. Questions on that? Because I know sometimes that can feel a little bit confusing and a little bit overwhelming. Any questions on how to read it off the periodic chart? Or how to build these configurations? No? Okay, I'm going to give you a couple to do then. And I want you to do the full expanded electron configuration. And then I also want you to give me the abbreviated. I want you to do both. So, excuse me. Do sulfur. Do, I don't want to do silver because, yeah, I don't want to do silver. Cobalt. And iodine. So full and abbreviated. Oh, I guess, do we end at 10:45, don't we? Yeah, I think so. Okay. I'm going to do sulfur real quick, and then we'll revisit these other two next time. So sulfur, I like to put my finger on it on my periodic chart, which I'm doing right now. And then I just know I have to go across, like reading a book, until I bump into sulfur. So the first thing I have to fill is the 1s, and I fill that completely. Then I go to the next row and I fill the 2s and I fill it completely. Then the 2p and I fill it completely. Then I move to the next row, I fill the 3s and I fill it completely. And then the 3p and I fill it with 1, 2, 3, 4 electrons. So y'all seeing how like it's the same onion layering filling every single time. It's just a matter of remembering the ordering of it. If I was to abbreviate sulfur, well, I could abbreviate it with the noble gas before, which is neon. So I'm going to take this whole chunk here, and I'm just going to replace that with neon. But then I have to add the remaining stuff. So 3s2, 3p4. So we'll stop there. We'll we'll do these next time. Somebody remind me if I forget, we could do those. And I will see you all on Wednesday. If you have any questions, hang out. Otherwise, enjoy the rest of your day, and I'll see you next time. Bye-bye.